What is quantum error correction in fault-tolerant quantum computing? Imagine trying to keep a delicate glass sculpture steady in a storm. That's similar to what quantum computers face with their fragile qubits. Quantum error correction is the method that helps keep these qubits stable and reliable. It is a set of techniques designed to protect quantum information from errors caused by noise, decoherence, and hardware imperfections. These errors can happen during calculations, making the results unreliable if not fixed. Quantum bits, or qubits, are very sensitive because they can be affected by their environment. Errors like bit flips, where a 0 becomes a 1, or phase flips, which change the quantum state's phase, can happen easily. And like classical bits, qubits cannot be copied directly because of the no-cloning theorem. So, quantum error correction encodes logical qubits into multiple physical qubits, creating a kind of redundancy. This way, if some qubits get disturbed, the overall information can still be recovered. In fault-tolerant quantum computing, quantum error correction codes spread the information of one logical qubit across many physical qubits. This allows the system to detect errors without destroying the quantum state. The process involves encoding, which creates the protected logical qubit, syndrome measurement, which detects errors without collapsing the quantum state, and decoding, which corrects any errors found. These steps work together to keep the computation on track. There are different quantum error correction codes, each suited for specific needs. The Shear code uses 9 physical qubits to encode one logical qubit and can fix both bit and phase errors. The Steen code uses 7 qubits and is fault-tolerant, meaning the error correction process itself doesn't introduce new errors. Surface codes arrange qubits on a 2-dimensional grid and have a high error threshold, making them promising for building large, reliable quantum computers. Fault tolerance means designing quantum gates and operations so errors don't spread out of control. Even if an error occurs during a gate operation, it stays localized and can be corrected. Combining quantum error correction with fault-tolerant gate design and better hardware makes it possible to run complex algorithms reliably. This is essential for tasks like factoring large numbers or simulating molecules, which requiring many qubits and long calculations. Without quantum error correction, errors would pile up quickly, making long and complex quantum computations impossible. It acts like a safety net, catching errors as they happen and fixing them in real time. This way, quantum computers can perform more accurate calculations and handle larger problems. In short, quantum error correction is the backbone that supports the development of practical, reliable quantum machines. It turns fragile quantum information into a resilient resource, making the dream of fault-tolerant quantum computing a reality.